Thank you for introduction, and it's also my honor to be here and to be physically here. So today my topic is symplectic excision, and this is a joint work with Yao Kashong. And I have to say that maybe before I start doing this presentation, I need to explain maybe I need to explain the title of this talk. So basically, the question we are going to discuss today is given a right. Yeah, this is kind of long work. I got the question from Anna Weinstein when I was in UC San Diego under supervising of Alvaro Pelayo, and then I continued. But this is I think the major process. The first major process arose when I was a postdoc at Cornell with Rayer, and then we finally make a lot of new progresses when I came to U of T, and and some even more progress after I come back to China, and we discussed online. So the question is, if we have a symplectic manifold M omega and a closed subset. So can we find a symplectomorphism phi that connects the complement of that with the original manifold M? So this is basically we can it's an existence question of symplectomorphisms. So of course this is a sub problem of the problem of classifying symplectic manifolds by symplectomorphisms. And I got this question from Alan Weinstein a few years ago, but this is not the original form. So the original form of the question was can one remove a ray from a symplectic manifold symplectomorphically? Okay, and this is the first part. The second part is what kind of closed subsets can be removed smoothly? And third question, how to derive a symplectic excision from the smooth excision. So now it comes to mind that we actually have we have different names, different adjectives before the excision, and actually we have much more. So actually we have a hierarchy of excisions. So how are different kinds of excisions related to each other. And finally, so we're going to show some examples. That can be excised or not in certain ways. Okay, the period. So first, the question by Anna Weinstein, and it showed up in the paper of him and Bachmann, that on algebroid, on the Hamiltonian Lie algebroid, that if R is the image of a proper embedding of the ray. So the ray is simply the half-closed interval 0 to infinity should be a non-compact symplectic manifold. So is there a simple homomorphism between M and M's R? So in my joint paper with Yao, we gave an answer to this question, but this question, there are other answers, and one of these is given by Stratman. So yes. Maybe some other answers, but we don't know. So now I will write down our answers. And that's actually a simple answer. So in our method we do not start with a general symplectic manifold, but we will consider first answer the question when M omega is the Cartesian space with standard symplectic form, but let me write down the coordinates x1, y1 through xn, yn, and omega can is dx1 wedge dy1 to dxn wedge dyn, and this the ray is image of the map from S to 0, 0, and xn becomes S plus 1 and 0. Okay, and the simple answer is we just define a smooth function f. Oh, it's too low to. Oh, yeah, right. Yeah, we definitely need to pick up a function, a bound function from M, from this R to N. And we find a function, smooth function f, which will be our Hamiltonian function. And with very explicit formula, Sn squared divided by 1 plus x1 squared all the way to xn minus 1 squared times xn squared. But we need to multiply by the bound function. And multiply by yn. Okay. So let's take a look of at this function y, and why is this? Oh, I will claim that the time one map of the Hamiltonian vector field of F sends R to N minus R to R to N. And definitely should be symplectomorphically. With a proper choice of, with a good choice of the sign, with a chi, the good choice of chi. But let's specify the choice is when we go through the proof process. But I would like to draw a picture of the R to N. So this is a 2n-dimensional symplectic manifold. And yn, so the spatial yn, the spatial coordinate, and yn equal to 0. When yn equal to 0, this is a hypersurface. It's a co-isotropic hypersurface. And on that hypersurface, there is a characteristic foliation in the direction of xn. Okay, do we have any color chalk? Yes. Our ray is on that hypersurface. So this is, the ray is given by all the other coordinates equal 0, and xn greater or equal to 1. I'm not sure if I'm going to call, let's call, just abbreviate by p x1, y1 through xn minus 1, yn minus 1. Okay. And now we actually calculate the Hamiltonian vector field. It's actually it's complicated in general, but it's very simple on the hyperplane. So as simple as you copy everything in the front. So actually this is p mod square times xn squared and chi, and replace yn by d xn. So this is indeed xf is indeed in the direction of the foldation, and that's because the hypersurface is lies on the 0 level set of f. So well, and if you analyze this, so this vector field it's going in a direction of d by dxn, but it's going in different speed. So our design, this vector field is going faster on the line p equals 0 and slower on the other lines. So you can check that if and p equals 0, this is simply xn squared chi times d by dxn, and by a standard ODE, you know that it precisely excites the ray r by xn greater or equal to 1 sent to infinity at time 1, and when p is not equal to 0, that it's a slightly difficult to calculate, but if you get rid of this chi, this guy, you know that you can still calculate the flow of this guy explicitly, and that would be a complete one. So there's a simple comparison. It's positive or non-negative and less than or equal to x. And the latter one is a coefficient of a complete vector field. It's complete. So implies that xf is complete there. Okay. Since things are less explicit away from this hypersurface, but there are two cases. So if f is non-zero at some point, this means that is the point that they call the point Z. The point Z lies in a non-zero level set of F. And by design, F is designed to be vanishing at infinity. Then this level set is compact. So we know that the flow line must last forever. Z and the flow, Z and the flow line of Z lies in the non-zero level set. But if F of Z is equal to 0, and we know F is some function times chi times Yn, and Yn is not 0. So either the first factor equals 0 or the second factor equals 0. Let's say so if the second factor equals 0, the chi equals 0, then by our design, whenever chi equals 0, d chi must be equal to 0. So this the df equals 0. I kind of forget this part of argument that if the first factor equals 0, the df must also be equal to 0, but I kind of forget the argument. Sorry. So we should get df equal to 0 there, and that's everything. That's everything. So we do need to add some the assumptions that add chi to be vanishing at infinity, and whenever chi equals to 0, d chi must equal to 0. Okay. Oh, okay. I need to say. And chi should be supported in a neighborhood, of this R. Yeah. Okay. So now this xf, the trajectory of xf is complete everywhere else except on this line. F vanishing at infinity. Yeah, I still don't remember some details, but the idea is like, so the point, how do I, so the time one map phi cannot be defined on this if xn is between 1 and infinity. So finally, the time one map phi is a symplectic homomorphism from R to n minus R to R to n. So that's our method and our result. And if we look at our argument, we have done much more. We have done a bit more than what we were asked. So we were only asked to find a symplectic homomorphism, but now we are going. We got a. I don't know if I can safely say that, but we get a Hamiltonian symplectic homomorphism, and so this is given by, this is Hamiltonian. And moreover, this is given by a time-independent Hamiltonian vector field. Thirdly, this is localized because we asked the chi to be supported in a small neighborhood of R, but this neighborhood can be chosen arbitrarily small. And last but not least, Z is contained, R is contained in the zero set of F. Okay, this is first observation. And another observation, if we look at this, our construction, we have a Hamiltonian vector field on the symplectic manifold. But on the hypersurface, if you look at the hypersurface, this is merely a smooth manifold or pre-symplectic manifold with a one-dimensional foliation. So hypersurface and V, let's say V is a restriction of XF on N, give you a null vector field. And the time one flow of V is actually, we'll say, a smooth excision of R from N. So you can do it in the other direction. So first we consider a smooth manifold with some foliation, and we construct a smooth vector field on that, and then we find a way so that vector field will excite the set we want to excite, and then we will try to extend that vector field to a Hamiltonian vector field on the ambient manifold. And we like the the part on the right, because this is not too, it's not in symplectic geometry. So everyone who have learned the smooth manifold and classical ODE would understand that question. And that's, so it's very surprising to us that why this method has not been used before. So we'll recall some undergraduate ODE courses. So we consider M. Oh, sorry, N. So we use N for smooth manifold. With X vector field, but here we do, when we look at the flow of X, we do not we do not require X to be complete. If X is complete, things are very boring. We look at incomplete vector fields. And now the trajectories of X would not necessarily have domain R, but an open subset of R, open interval of R. And the trajectory is just in solution of this ODE problem, d gamma over dt equals x at gamma t. So and we say for any x in this N, okay, for any through any x, there is a solution with the initial value problem, gamma 0 equal to x. So, and we can define the flow domain. Dx has the form xt with s x less than t less than t x. And dx must be an open subset. And so therefore Sx, the backward exit time, and Tx, the forward exit time, must be upper semi-continuous and lower semi-continuous. And you can see that this semi-continuity is exactly equal to the openness of dx. But now, this will generate actually a family of diffeomorphisms. Phi would be a diffeomorphism from the set of Sx less than -1 to Tx greater than 1. So if we really want to find a V whose time one flow excites the set, the prescribed set, we only need to design the sub-level set of and the super level set of the backward and forward exit time functions. Okay, and this is for a time-independent vector field, and for time-dependent vector fields, we have a more complicated definition that will still that maybe change in our final version, but this is our current version of this definition. So the difference from the standard one is that our vector field x tilde is defined in merely a subset of n cross 0, 1. And for any t0 and x in W, so not, sorry, x t0, there is a trajectory through that point in time solving exactly the same ODE with initial value gamma t0 equal to x. And if we write W to be a union of, so the slices t from 0 to 1 cross t, and then we must have the W0 to be n minus z. So okay. So this part corresponds to this part. Oh no. Here we ask gamma to be from the entire 0, 1. So this is a change of the definition for the time-dependent vector fields. Yeah, we choose a part that it is defined through. So we can't ask it to be defined on all n cross 0 to 1 and to be from 0 to 1. This is impossible, but we made this. Yeah. This is a requirement. Under this requirement, the time-independent thing is a special case of that time-dependent definition. I should say, okay, maybe. Yeah. So far I'm talking about our method to generate the smooth excisions, and then we give a theorems from smooth excision to Hamiltonian excisions, and that would produce the conditions you want to see. This is not some manifold, just any closed subset. And the condition is it is closed and maybe not empty. Yeah, so yeah, with this assumption, so here we can actually find the time 0, 1 map. It's from W0 to W1. So in the time-independent case, if we require Sx to be greater or equal to -1 everywhere, okay, which would imply that Xx is I think I may mess up something over here. It's, but this is not correct. T is greater than 1 and Sx less than -1. So if Sx is greater or equal to less than -1 everywhere, so imply that Sx is -infinity everywhere, and Tx less than or equal to 1 precisely on that, then phi would excite z from n. So that's how you construct a smooth excision of a time-independent vector field. Time-dependent ones, well, we will require simply W0 to be n minus z and W1 to be n. then phi would be an excision. In our current version, we also add another technical assumption, which I do not know whether we should put it in the final version though. But this is a case of the time-independent case. Okay. Maybe I should or should not draw some pictures to explain this. It's easy, but it's not very familiar. And let's say n to be -1 to 1, and if the simplest case, one-dimensional case, x to be d by dx, then x would be how far it comes from -1, so it's x plus 1, and tx would be just 1 minus x. So the set of t greater than 1 is this part. So basically, you're just moving. So this is time from 0 to 1, and you're just moving from left to right. Oh, yeah. So you're simply moving from left to right. And these two triangles are the triangle on the right will be killed, and the triangle on the left are newborn, so they cannot be in part of our diffusion Morrison. In that case, if you look for the time for the definition of time dependent one, our W is this parallelogram is our W, but in that W, every trajectory is complete. So that's how we define them differently. Okay, so so actually, this one-dimensional model is already very interesting. Yeah, this is simple, but it's interesting. So here the x, if x is a slightly more general, x the general case, x is Vx times d by dx, and Vx is a smooth function from -1 to as a positive, a non-negative smooth function. And now you can easily calculate that Tx by the Barrow's formula. Barrow, the advisor of Isaac Newton, from x is simply an integral of the reciprocal the way I'm writing is not quite right, because it may happen that some v xi is equal to 0 between x and 1, but in that case, just set it to be infinity. So, and now all you can see is that this t function is decreasing time. Okay, okay. Oh, and that. Okay, so what we can get is lemma. If sigma is a manifold, and lambda is a lower semi-continuous function, then we can find there exists a smooth vector field with coefficient v such that the set Tx less than equal to 1 is precisely the epigraph of lambda. So we do construct a smooth vector field that excites the epigraph, a closed epigraph of the LSC function, and our result would be Sure. I'm writing our main theorem. Yeah. So given this smooth excision result, we can show that if Z0 is a closed subset in a smooth manifold N0, and X0, that smooth vector field on N0 and U0 is an open neighborhood of Z0 in N0 such that and I is an embedding of U0, but is proper restricted to Z0 such that it sends the vector field X0 to a null vector field on M, symplectic manifold M, then you can find a smooth function f whose Hamiltonian vector field, the time one map, time one flow of the Hamiltonian vector field would be our symplectic excision.
You're assuming that X0 excises the.
Oh, yes. And assuming that excises Z0 from N0. Yeah. Sorry, the time is up, and there's something left that had not been talked.